Let's now take a look at review problem 4.5, trying to find the best fit of the model of the data to the model y equals square root of a plus bx cubed, where presumably there is some physical reason to think that such a model would be appropriate. Let's plot this real quick in Excel. So scatter, and we see that this is not a straight line. It's clearly got a curve to it, and so something ought to work besides just simply um, besides the linear fit. Okay, so the hypothesized model is y equals square root of a plus bx cubed. So to make this into something that is intrinsically linear, let's square both sides. Y squared is equal to a plus bx cubed. And so now there's two different transformations that we ought to do. Let x prime be equal to x cubed, and let's let y prime be equal to y squared. And by making both transformations, we get that y prime is equal to a plus bx prime, which is something that is linear. And so we have a linear model now, and so the original model was intrinsically linear. Okay, so practically speaking, let's get our x prime and y prime, and we get this. The x values have to be cubed. A2 cubed. So I cube all the x values, and I square all of the y values. And then when I plot this, I do get something that looks decently like a straight line. So if I add the trend line, and let me put the equation of the trend line on. So the slope is 2.051, whereas the intercept is 996.96. So 2.051, so that is going to be the slope. And the intercept was 990 something, 996.96. So I just read off the values of a and b. There's no transformations that have to be done for these variables in this case. And so we finally get to our equation y is equal to square root of 996.96 plus 2.051 times x to the third. And the same kind of calculation can be done with Excel as described in the other videos that go along with this review.